This video will show you how to set up some problems using elasticity theory. The physics that we'll use is right here, solid mechanics. So we'll add that. And I'm just going to use a stationary study. So we've got the physics in here, and I added a square geometry, just 1 meter by 1 meter. This is the default. So we need to set up some parameters, and the three main parameters that we need here are the elastic modulus, and so I'm going to use a modulus of 1 gigapascal, which is about the modulus of, say, a soft rock, and 0.25 would be a reasonable Poisson's ratio, and density, let's say 2,700 kilograms per cubic meter. So these are properties of rock. If we wanted it to be metal, it would be a bit higher modulus and density. But this will serve for our purposes now. So this will be an elastic analysis. We've got the properties and we need boundary conditions. So the default is just that the boundaries are free. So they're stress-free, that's what that means. Initial values, zero displacement and velocity, and so that'll be okay. We need to put in some boundary conditions for our problem. And so the first thing that we'll do is say, okay, here's this block, and the block is resting on the ground, and we're going to load it by pushing down from the top. So we need to constrain the bottom boundary. So I'm using a fixed constraint on the bottom, and that's going to have an equation so that right here, this is the displacement vector is equal to 0. So there's no displacement at all along this bottom boundary. And then along the top boundary, we'll use a boundary load boundary condition. Specify that. And we're load as force per unit area, so that's stress, and we're going to have the load in the minus y direction, and we'll say it's minus 1 e to the 6th 1 megapascal. And that's all we need for an analysis. We'll check out the mesh. Okay, that's the default mesh. That seems reasonable. We'll go ahead and run it, and this is the result. The default is the von Mises stress. Let's take a look at the principal stress, the third principal stress. We're compressing the sample here, and so we'll take a look at the third principal stress, which is the most compressive stress. And what we see is that we've applied a stress of minus 1 times 10 to the 6th pascals, and that's this bright red color. So right up here, that's the applied stress, and you can see that most of the block is fairly red, so most of the block is in the range of 1 megapascal. But if we look carefully, we can see, well, down here in these corners, we have quite a large, well, it's 1.7 or so times, almost double the compressive stress right down here in the corners. And then we have this darker red right here and right here that's actually a bit less compressive than the applied stress. And so what's going on here is that when we push down on this block, it's bulging out laterally, and you can see that right in here. The block compresses vertically and bulges out horizontally. The boundary condition prevents it from bulging down here at the bottom, and we can see that if we zoom in on the corners. And as a result, we get some stress concentration here at the corners. The bulging out here laterally causes this edge to bend, and as a result of bending, we're reducing the compression because we have this outer edge that's it is now curved. Okay, so that's our first simple result, and we could envision a situation where this would occur. We could have a block and put some extra weight on it and cause this deformation. I should also point out that the deformation here is been amplified. The default is to have this deformation with a default scale factor. If I make the scale factor just 1, then this is what I get. And you can see that the deformation is really quite small here, because if I show it to scale, there I can see a little bit if I zoom in. But if I show it to scale and I take a look at the whole body, then it's really hard to see anything. And that's consistent with this being an elastic analysis where the strains are now small. Let's change the analysis and see if we can get the stress field to be more uniform. These concentrations of stresses in the corners were a result of the constraint boundary that we used at the bottom here. So we're going to go and remove that. And instead we're going to use a roller boundary. So we'll select this bottom boundary. And the roller boundary, as we can see from this equation, requires that the displacement, u, normal to the boundary, is equal to 0. So what that means is that we can't have any displacement along this boundary in that direction, which is what we want. But we're removing the constraint in this direction. So we can have movement in this direction, which is kind of what we want, because if we push down on this, we saw that it expands out laterally, and we'll also want it to expand laterally down here. That should remove this stress concentration. So this all seems good. If we go ahead and run it, though, we'll see that in fact it's not so good. There's an error, it failed to find a solution, and it's kind of cryptic what it says here. What the problem is in this case is that the boundary conditions are not constraining the motion of this block. So in this case, this block would be free to move in this direction. This is like ball bearings here on the bottom of this, or rollers. That's the name of the condition. So the block could move this way, and there's nothing to prevent it from just heading on down the road. And so that's why we can't get a solution. So what we can do is put rollers here on the side. And if we run it this time, we'll see that it does run, and it gives us this result where the stresses are uniform and equal to 1 times 10 to the 6, 1 megapascal, which is the applied stress. Okay, so this is kind of what we were thinking that we would get with the first analysis, but because of the way we set up the boundary conditions of the first analysis, we got a different effect. But now here we are, and we have this effect where we can load a block and get a uniform stress distribution. Okay, so now I want to try a different kind of load. This one will be the kind of load that's produced by the weight of this block. That's a body load, and we can include that by putting a body load in the solid mechanics module, and I'll show you how that's done in just a second. But first, let me just point out that I included a variable called rho because we'll want to use that in the body load. So I go here to solid mechanics and select the body load node right there and put it in, and we'll just put this block here. And so the body load has a direction and a magnitude, and this is a force per unit volume, and the force per unit volume is the unit weight of the material. And so this will be the density times gravity. So this would be rho times, and we can go g constant. I could define a variable that's g, but there's something, a variable called g-const, that is the gravitational constant that's built in. And the gravity is going to act in the negative y direction for this problem. So I'll put it in like that. And I'm also going to take this boundary load off the top. Okay, so let's see, I can go ahead and run that. See how that goes. I still have the same roller boundaries in there from last time. And so here's what I get. Here are the displacements, and you can see that, or this is the third principal stress. So these are the compressive stresses, and you can see right up here at the top, the stresses are essentially 0, 10 to the minus 11, and then the stresses increase as we go downward to this value, and that's just from the self-weight of the material. Okay, we can see some displacement that results from this deformation amplification that we get in the plot. And it's just moving straight down. So this is the kind of thing that we might expect to happen if we had a piece out of a very broad area, and the rest of the material that we're not really considering prevents there from being any lateral strain. So you can see that we don't have any lateral strain here, and that's what the roller boundary does. But we might also be interested in a body that is deformed under its own weight, that bulges out laterally. So we'll do that by removing these roller boundaries, and we'll just go back. Well, let's just, instead of removing it totally, let's just disable it. And let's just go now back to this fixed constraint boundary that we had a little bit ago. And let's try now running this. So this will be the deformation from a body load that is has no constraints on the sides. And let's see, we can see here where it's bulging out a little bit on the side. And we can increase the scale factor to show that bulge and the general deformation a little bit better. So I've got 18,000 or 8,000. Let's go to 15,000. And there's the shape. We can see that bulge a little bit more. And this is the plot of the stresses, but we might also be interested in a plot of the displacements. So if we go back here, we can just change this stress plot to the displacements. And if I go here to solid mechanics, displacement, I get a couple of options. The displacement field, this allows me to plot the x, y, and z components of displacement, and then this one right here is the total displacement. So right now let's just take a look at the y displacement. So here it is. It goes from 0 is the maximum, and minus 12 times 10 to the minus 6 is the minimum, but you see we've got this sign factor here. So the negative displacement means that it's moving in the negative y direction, so it's moving downward. So the largest displacement is here in the blue, and we can see that the magnitude is, everything's multiplied by 10 to the minus 6, so this blue corresponds to 12 microns of displacement here along the top. So that's how much displacement this block experiences due to loading by its own weight. Now we're ready to modify the geometry a little bit and see what happens. The first thing that we'll do is to take a look at the stresses around a hole. And so I've changed the model so that we're now using the roller boundaries on the three sides. That's done here. And I have a boundary load. And what I want to do is have the boundary load be tensile. So I want to pull up, and I'll do that by changing the sign here. And let's just take a look at that. We'll run it just real quick and see if it's doing this thing that we are expecting. Yeah, so there we go. Well, that's actually a good bit more deformed than what I was expecting. So let me go and just use the default scale factor. that still is pretty excessive. So let's see. There we go. That looks better. So we can see that it's clearly tensile. It's extending in this direction. And so that's pretty good. Let me just go up here and check boundary load. So we have a boundary load of 1 megapascal, and okay, still the same moduli, so everything looks good. So now what I want to do is modify this by putting a hole in it. So I'll go to a circle, and let's put a circle in this plate that is 6 inches in diameter. Oh no, I'm sorry. That's the x coordinate. We'll do 0.5, 0.5, and up here for the radius we'll put 6 inches in radius. Let's see what that looks like. Okay, so there's the circle, and we want this to be a circular hole. So an easy thing to do here is to use this Boolean operation, and we'll put here the square as the first object, and then we're going to subtract from that this second object, and we'll select that. And when we build it now, we have this hole in the plate. So now we can go ahead and run this. And there's what it looks like. Now remember, there's lots of distortion here, and I think probably too much. So let's tone that distortion down a little bit. How about there? Okay, so now we still have a good bit of distortion. We can see by pulling on this that we've caused the hole to become elongate. And we're also changing this is now the plot of the displacement. So displacements are increasing as we go up, and so that makes sense, but that's not really too informative. At least it's not informing us in a way that I want to show you. What's happening here is, or what we'll be interested in, is how the stresses are relocated by this hole. So I'm going to plot the first principal stress. This is the maximum tensile stress, and you can see here that tensile is positive, so the largest values here are right along the side of the hole. I'm just going to turn off this deformation and zoom in a little bit, and there we go. And so you can see we're applying a stress of 1 megapascal in tension, and that's this kind of bluish color. So let's see, right about there, that's the 1 megapascal. But once we get down in here, you can see this hole really causes the stresses to become redistributed. The largest stresses are right here, and then it decreases, and then down under here we can see that we have stresses that are even less tensile than what we apply. So this is kind of a shadow above and below the hole, and the stresses that were once in this area now go through this area, and so that's why we have an elevated tensile stress right here in this area. And you can see for this hole and applied stress that the maximum tensile stress that we get is 2.8 times 10 to the 6th, or roughly 2.8 times the applied stress. So we've got some amplification of the stress here on the wall of the hole, and then right down here we've got a stress that is essentially 0. Okay, that's right along this boundary. So even though we're pulling with a tensile stress of 1 megapascal, right here at the top and the bottom of the hole, the first principal stress is essentially 0. A plot that's useful when trying to visualize stresses is right here. If we go to more plots, and right there, go to principal stress surface, and there are a variety of settings here. We'll just use the default for now, and we'll plot the stresses. So what this plot does is make these little arrows. So that is a graphical depiction of the stresses. It shows the principal stress The maximum tension, this is the minimum tension or the third principal stress, and it shows the orientation. So you can see, if we zoom out here, you can see that the presence of this hole causes the principal stresses to rotate. These maximum principal stresses, the red ones, are roughly parallel to the edge of the hole. So out here they're roughly tangential, but you can see as we get over here, they're not quite tangential, but they're curving around to be to try to be close to parallel to the edge. And then you can see also, if we zoom in a little bit, the tensile stress here is reducing, and it flips around, and it's going to zero here as we get right to this point on the edge of the hole. So that can be a useful plot for trying to understand what the stress field looks like. Okay, now let's take a look at what happens when we change the shape of the hole. We can do that by going here to the circle. We'll disable that. And what I want to do now is add an ellipse. I guess I'm going to have to disable this difference calculation before I put the ellipse in there. And the ellipse that I'm going to put in here will be, it'll have the same, the semi-axis of the ellipse will be 0.15, the same radius as the circle. But the b-axis will be 1/10 of that, 0.015. And we'll use 0.5 and 0.5 to put the ellipse in the center of the plate. So there it is. And then we're gonna redo this difference calculation. And we'll select the ellipse to subtract. So now when we build all, we have this elliptical hole. So we'll go ahead and run this. All this stuff is set up the way it was for the circular hole, but we'll just keep it the same, and we'll run it for this elliptical hole. So here's the results. Just at first blush, it looks like we have a lot of blue there. This is the first principal stress. So this is the tensile stress, and it's low numbers for the blue color. But now remember, let's look at the scale. We applied 1 megapascal. That's 1 times 10 to the 6th. So this is 2 times 10 to the 7th, or essentially 21 megapascals. So this blue color right down here is the stress that we applied. And so it seems reasonable then that a lot of this plate would be blue. But remember, with the circular hole, we saw that we had stress concentrations. And we have that here, but it's just harder to see. And it's occurring right here at the tips of these cracks. And you can see that there's this red color. Well, you can see the yellow, I think, right there. That's 14 megapascals. And if we zoom in, we might even see that it gets higher than that. Yeah, so there's the red color. This 21 megapascals right here at the tip of this elliptical hole. And so what's going on here is that this ellipse is sharp, has a sharp, very small radius of curvature right here at the tip. And so when we pull on it in this direction, that concentrates the stresses even more than a circular hole does. You can see from these stress symbols that it also affects the distribution of the stresses above and below the crack, as well as out in front of the crack. Well, the elliptical hole. The way that this elliptical hole concentrates stresses is pretty profound. It's 20 times higher tensile stress. That will cause the material to fail preferentially right here at the tip of this elliptical hole. And as a result, elliptical holes like this one are often used to represent cracks. I was slipping earlier in calling this thing a crack because this is done so commonly that when I see an elliptic hole, I think, in my mind's eye, I think, oh, well, that's a crack. And so as far as a crack goes, this is quite exaggerated because cracks wouldn't be this wide. They would be much narrower. But we could make the elliptic hole even narrower than this. And if we did that, we would find that it would concentrate the stresses even higher. Keep in mind that when you're calculating the stresses around the tip of an elliptical hole where it's quite sharp, the mesh element size may really make a difference. And so this is the default mesh, and you can see that the elements here get much smaller than they are out here, but they're still fairly large compared to the size of the crack in this area. So one thing you should do for this problem, and actually for many problems, is to evaluate the effect of the mesh size. And you should calculate the results and then try changing the mesh size and see if you get the same results. If you don't, then you need to probably make the mesh elements finer until you get to a point where the results are not affected by the size of the mesh. So one thing you can do here is to go, let's see, this is probably what you'll see when you take a look at the mesh. And if you go here to size and then go to custom, then you can adjust the size of the various constraints on the mesh size. What I did was to adjust the minimum element size. I mean, what you could do, I think, what would be easy is to just change here to extremely fine, say. And we could do that, and there we've got some very fine elements, but all of the elements are here are smaller, and we might not really need them to be finer out here. So another possibility would be to go back here to normal and just reduce the minimum element size. And let's go 1e to the minus 5 and try that. And so there we've got some fairly large elements out here, but the elements around the cracked tip are quite small. And we could make them smaller if we like, 10 to the minus 6. And so that gives us a way to put fine elements right here around the cracked tip, but if we zoom out, we still have fairly large elements around here. There are various other settings that you could experiment around with, and in the end, though, you want to make sure that that changing the mesh size doesn't affect your results in an appreciable way. That way, your results will be independent of the mesh.